Hey there, physics fans. Today we're going to go through text problem 11-104. In this problem, as we read through it, we see that we're talking about a beam steerer for a particle accelerator. It's really interesting. If you want to see an example of this, feel free to go down to the basement of Bartlett Hall under room 174, and through the glass you'll be able to see a particle accelerator, and if you look, there is a region where we have a beam steerer. All right, for this problem we have a charged particle that is moving as it goes through a magnetic field over some distance, and we're tasked to find what is the angle, all right, what is this angle right here, once the particle leaves this region of uniform magnetic field. Okay, so our task, that was our read step. Our task is to find theta, and for our physics, all right, you should be thinking E and M as we go through this problem. Specifically, I want you to be thinking about the equation for the force on a charged particle as it moves through a magnetic field. All right. Additionally, since our magnetic field is perpendicular to the velocity of our particle, all right, we're not going to be changing the speed of our particle at all. We're just going to be changing its direction. And if you recall back to block 1, when an object's speed remains constant but its direction is constantly changing, all right, we can describe it as being a uniform circular motion. And with that, we have the centripetal acceleration is equal to the speed squared over the radius of curvature. And we'll be able to use that to help solve this problem. The next step is to do a drawing for our problem. We have a good start to it, but what I want to do is I want to add a little bit more information to help describe this uniform circular motion. And to start that off, I will draw the radius as my particle leaves. All right, so this is, the best of my ability, that is tangent. All right, and then I'm going to have the radius also from when the particle enters. All right, and in between those, I'm going to try to represent the motion of the particle as it changes direction while it undergoes uniform circular motion. Additionally, I want to draw a line here. All right, this is the variable d, or 5 centimeters according to the given information. All right, if I go through the geometry, I can see that this angle theta is the same angle of the arc that my object goes through, or my particle that goes through. Okay, for the givens for this problem, we're given that it's a proton, so we know its charge, we know its mass, we know the strength of the magnetic field, we know the velocity or the speed of our proton, and finally we know the distance that the width of our magnetic field. And assumptions, we're going to assume that we can neglect gravity. Since we're talking about a single proton, the mass is so small, we don't need to worry about the effects of gravity in comparison to the effects of the magnetic field on our particle. All right, and finally we get to go into the solve step. So to start off with, I want to start with the force on the charged particle as it moves through the magnetic field. All right, and I know that I'm going to be talking about uniform circular motion, so I want to find the magnitude of this force. So I want to evaluate my cross product. All right, I know it is sine of 90 degrees because the velocity of my particle is perpendicular to the velocity, or to the direction of the magnetic field. So sine of 90 degrees, I know that is going to go to 1. So that means that the magnitude of my force is equal to the charge times the speed times the magnetic field. And as I said earlier, we're going to be talking about this particle as it undergoes uniform circular motion. So recall that a force that causes uniform circular motion is going to be equal to the mass of the object times the centripetal acceleration. All right, well, it turns out that force is the same force. So, and I can describe that as the mass times the speed squared over r. Since these two quantities are the same, all right, set them equal. All right, and a little simplification going on there. So I have the charge times the magnetic field is equal to the mass times the speed divided by the radius. Now I'm not given any information about the radius, so I want to go back to my drawing and see if I can pull a relationship that gets me closer to the quantity I'm trying to find of theta. And sure enough, I can use that the sine of theta is equal to d over r. If I rearrange for and solve for r, e over sine theta. All right, so now I can take this quantity, I can plug into my equation down here. Now all I need to do is isolate theta. And I get my algebraic solution. Once I put my numbers into the calculator, I'm going to find that my angle is equal to 13.9 degrees. All right, but I only have one significant figure in this problem, so that's going to reduce down to 10 degrees. Now as I go through the check step, first I want to ask myself, is it reasonable? I expect as I go through a beam steer that the particle's path will change, and I see that it changes by a small angle. That is something that seems reasonable. All right, I've already identified that my problem has one significant figure. My answer has one. And then finally, I know that I don't have a vector quantity. It's a scalar. It's the angle of 10 degrees. So my check step is looking good. It is reasonable. The units in sig figs work out, and then it's a scalar. There you go. We have completed problem 11-104. I hope this was beneficial for you.